Hi students, I'm going to explain electron configuration with this video. Make sure you have your notes and the practice at hand. Okay, so electron configuration. We're going to have a little bit of background information for this. Let's talk a little bit about the isotope of hydrogen 1. If we remember from previous knowledge, hydrogen 1 isotope, 1 would be the mass number, so it would contain only one proton and one electron. So the proton that has a positive charge will be located in the nucleus, and the electron the negative charge will be moving around the nucleus. This is a diagram that shows Bohr's model of the hydrogen atom. He thought that electrons moved in definite orbits, just like planets moves around the sun. But there was a problem with this concept, and by the mid-1920s, scientists became aware that the Bohr model didn't work for all the other elements. It only worked for hydrogen. So they had to be some modifications. So the best modification, well, one of the best was the one made by Erwin Schrödinger. He developed the electron cloud model. And this one would be like, imagine that you're taking photos, multiple photos of the electron of hydrogen moving around the nucleus. And then you overlap all these photos, and this is what you will see. So that's what he called the electron cloud model. Later, another scientist, Heisenberg, he determined mathematically the area or the region in which these electrons will most likely be found, and they call these regions orbitals. So now, with this new knowledge, now scientists realize that the 1s orbital is not a Bohr orbit. It doesn't go in circles around the nucleus. It's more like an area, right? So, but this theory of the orbital doesn't give us information of the path that it is taking. We just know the most probable location of the electron. So, as we mentioned, the photos of the locations overlapped. Scientists decided that 90% of the total electron probability was enough. So the 1s orbital, the one for hydrogen, for the electron in hydrogen, is the radius of a sphere. Remember that we have to think in 3 dimensions. Radius of the sphere that encloses 90% of the total electron probability. So the orbital that corresponds to the lowest energy possible, it's called the 1s orbital. And this is another representation in which we show a sphere to be accurate with the 3D location. So let's start with electron configurations. Electron configurations is like giving the address of the electrons. I'm going to do an image or an example where, like, if I ask you for your address, you're going to tell me the address of your home. If we want to be more specific, you're going to let me know if you're in the living room, or in the dining room, or in your bedroom. So kind of like that is this concept of electron configuration. We're trying to give or know the address of the electrons. So the orbitals that we already started to talk about were the s orbitals, where the shape is a sphere. The difference between the 1s and the 2s and the 3s, it's only its size. The 2s orbitals can hold 2 electrons. So think about it as a room, a bedroom with 2 beds, enough space for 2 people, 2 electrons. This would be a 1s, a tiny bedroom. A 2s would be a bigger bedroom, but it can still only hold 2 people, 2 persons. And the 3s would be a much, much bigger bedroom. It can have an office or more area to move around, but still only 2 electrons or 2 persons are going to be in these s rooms or s orbitals. We also have p orbitals. Now that shape is not a sphere. It's like a dumbbell, like the ones that you use for doing exercise, for lifting weights. And these dumbbells are located in the X, in the Y, or on the Z um, axis. And you can think of them existing together, like overlap, like I show here. There exist also d orbitals, which are much more complicated, and f orbitals as well. But don't worry too much about the NF, just the concept of spaces. So let's start explaining or learning how to do electron configuration. So again, it's like finding the address of the electrons. So first we must learn some basic rules. You can pause the video right now to take notes. The first rule is Arbaugh's principle. Just the same as protons are added one to one to the nucleus to build up the elements. Remember, as in the previous knowledge when we saw fusion, it's one by one, the elements start growing one by one proton at a time. Similarly, electrons are added to these hydrogen-like orbitals, the ones that we just saw before, and the orbitals are filled up in order of increasing energy. What is this energy? What does this mean? Well, it's the energy that it takes the electrons to move around the nucleus. And okay, so this Arbaugh's chart, you have it in your note taker. This is the chart that is going to tell us the order in which the electrons are going to be filled up. So what does this chart mean? You have in your note taker a chart where I place the Arbaugh's chart, and besides I place you some notes so you can do some labels. So these numbers, 1, 2, 3, these numbers from 1 all the way to 7 represent the energy levels. They're called energy levels. The letters S, P, D, F are called sublevels. And then every sublevel has a specific number of orbitals, as we're going to see in a moment. For example, the S sublevel has a single orbital, and it has space for 2 electrons. The P sublevel has 3 orbitals, and it will have space for 6 electrons. The D has 5 orbitals, and the F has 7 orbitals. The superscripts that we have here, these 2, 6, 10, and F, are the maximum number of electrons that these areas can hold. Okay, we're going to go to the next rule, Pauli exclusion principle. An orbital can have 2 electrons, and if they hold 2 electrons, these electrons must have opposite spins. I'm going to explain this, the concept of the spin. Okay, if it only has 1 electron, it's called a non-paired electron. If it has 2 electrons, now we're going to have them in pairs. Electrons are negative, so they repel each other. They would like to be as furthest away possible to each other. Imagine that they're like enemies and they don't like each other. So they're going to try to be as far away possible from each other. So if one spins to the right, the other one will spin to the left. So if you have a single electron, an unpaired electron, you can do the orbitals in boxes or in lines, as we're going to see later, and you're going to place one arrow. The arrows represent electrons. So a single arrow for an unpaired electron, or 2 arrows to represent 2 electrons. The reasoning behind this is as electrons move in opposite directions, their magnetic fields will cancel, and that's how they can be in the same space, avoiding too much repulsion from their negative charges. Okay, and the last rule is Hund's rule. The lowest energy configuration for the atom is the one having the maximum number of unpaired electrons allowed by the Pauli principle in a particular set of orbitals. I'm going to explain this in a moment, so don't get Don't worry about the wording, about the fancy wording. It's very easy, in fact. Imagine that you rent an apartment, and that apartment you go to, I don't know, La Isla or wherever, and that apartment has 3 bedrooms, each bedroom with space for 2 persons. So you invite your friends. Imagine that you're going to label them PX, PY, PC, these 3 bedrooms. Imagine that you arrive at the hotel, but at the apartment first, an Airbnb or whatever. So you arrive and you're going to choose the best view, maybe the one that shows the beach or whatever. So now another friend comes and now he's going to choose the next room, right? To be more comfortable, everybody has its own bedroom. So that would be the orbital diagram for 2 electrons in this level. If another friend arrives, then each of you will be in one bedroom each to be more comfortable. Now, if a 4th guest arrives, then you have no choice but to share one bedroom. The other 2 will remain with single people or single electrons. If there's 5 persons in the room, then you will have no choice but to share. And that will be the maximum occupancy of this apartment, right? 2 people per room. Okay, so this is what these rules mean. Okay, so let's start following this. Let's start doing an example and explaining a little bit more the Arbaus chart. Suppose that you're in charge of that apartment building and you're going to rent it. But so the owner gives you the keys, but you're also in charge of cleaning the bedrooms, all these apartments. So what are you going to do? Imagine that these numbers 1 through 7, the energy levels, are the levels of the apartment. So the level number 1 is ground level, the easiest to clean because in fact your room is also on ground level, and you have there all your cleaning supplies. So if guests arrive, you're going to open first the 1S apartment, right? Because it's easier to clean. If more guests arrive, you're going to open the 2S, second floor, only 1 bedroom, just because it's less energy. The same reason is less energy. It's like comparison. The electrons need less energy to move in s orbitals than in p, and than in d, and than in f. So that's why they go in these energy levels. So you open the second room. If you run out of rooms and you still have more electrons, then you open the next level. You open the 2p, which will be on the second level, but now those apartments will have 3 rooms, enough space for 6 people, and so on and so forth. Then you open this room that is on the 3rd floor with 1 bedroom, and then here is when it starts becoming a little bit tricky. You open the next room, which is in the 3rd floor with 3 bedrooms, enough space for 6 people. And then instead of opening the room in the 3rd floor that has 5 bedrooms, you decide to open one in the 4th level. Why? Because it only has 1 bedroom. So for you, it's less energy to go up a level than to open a room with more bedrooms. So in the same comparison, less energy is needed on a 4S than in a 3D. So you finish all the arrows before going to the next level. So 4S and then 3D, 4P, 5S, and so on until your last energy level and sublevel will be the 7P. Okay, we're going to practice. Don't worry about this too much. You will have the chart with you the whole time. So let's start. Let's practice the electron configuration for sodium. If you have a periodic table, locate sodium in the periodic table and you will see that it has an atomic number of 11. As we know, those are the protons. Since sodium is a neutral atom, it will also have 11 electrons. So we must give the electron configuration or the address of those 11 electrons. So we're going to start right here. We're first going to do electron configuration in the format of orbital diagram. So we're going to open an orbit, a room, which is going to be labeled 1s. We're going to start here. So here there's room for 2 electrons. So we place 1 electron facing up, 1 electron facing down. That's it. We're done with this room. We cannot have more people in there, more electrons. So we open another room. We finish this one. We go to the 2s. The 2s again has space for 2 electrons. So up and down so they can have opposite spins. We're done with this one. Now we have to open another room. How many rooms do we need to open? As many as we need to fill the 11 electrons. Okay, so we have to keep going. Now we open the 2p. In the 2p, you must place the 3 lines or the 3 boxes. It's like in the house, you have 3 rooms. Even if they're empty or they're full, the 3 rooms exist. So you must show all 3 orbitals whenever you work on p sublevels. Okay, so now you're going to fill up more electrons. Right now we have 5 electrons total. So we keep going, 6, 7, 8, 9, 10. We're not done and we need an extra room because the P already has the 6 that it can hold. So we open another room, which would be the 3s, and we only need a single arrow because now we have already the 11 electrons. We already consider the 11 electrons. Another format for electron configuration is called SPDF notation. And the only thing that you do is you do the same, 1s, and now instead of arrows, you place the number as superscript for as every single sublevel. So you will have 1s2, 2s2, 2p6, the 6 arrows, 3s2. Another notation or another format for electron configurations are what it's called noble gas notation. If you go to the periodic table, you will notice that the noble gas that is previous to sodium, it's neon. Neon has 10 electrons. So it would be as if we are going to consider all these up to 2p6 in the brackets. We're going to consider 1s2, 2s2, 2p6 as the neon. And then outside of the brackets, we are going to place whatever is missing, in this case, the 3s1. Why do we use noble gases in the periodic table? The noble gases for the elements are like the heroes. So all the elements want to be as noble gases. That's why we use noble gas notation, which we're going to see in more detail later. Remember to use the previous noble gas, the one before of the element that you're working on. Okay, so once you have the SPDF notation, then it's very easy for you to do the Bohr's diagram. Even though the Bohr diagram is not the best representation, we still use it in chemistry because it shows the energy levels and the number of electrons. So for Bohr diagram, you can place if you have the specific isotope, you can place the protons and the neutrons. If not, you can just place the symbol Na on the center on the nucleus, showing the nucleus. And then the first circle is going to have, in this case, 2 electrons. The second circle, which is representing the second energy level, you have to place 8 electrons because the 2s and the 2p are on the same energy level, which is represented here on the second circle. And then lastly, you will have a third circle with 1 electron, which is representing the third energy level with a single electron. That's Bohr diagrams where it would just show all electrons in the specific energy levels. Then lastly, you have Lewis structure or electron dot structure that shows only the valence electrons, which are the electrons on the last energy level. So you just place the symbol and a single dot. Okay, we're going to do a big one. We're going to do electron configuration for Mercury. This one comes on your practice, so you will have the answer in here. So if you go to the periodic table for Mercury, you're going to notice that Mercury has 80 electrons. Again, you must follow the arrows, be very careful, especially here when the pattern is not so obvious. And you're going to have, we're not done here, you're going to have all these for SPDF notation. So you're going to go room by room or level by level, opening, and you can, I'm sorry, I forgot to mention that you can omit the orbital diagram for this one because it's huge. I'm not making you do 80 arrows. But if you go slowly, arrow by arrow in levels, this is going to be the SPDF notation that you will end up with. Notice the level, for example, here after 3P, then you go to 4s2, there it is. Then you open 3D10 and so on. 4P6, 5s2, 4D10. So you follow the arrows. You follow the arrows until you stop in 5D10. How do you know where to stop? When all the superscripts add to 80, in this case for Mercury, or in the electrons that you're solving for the particular element. Okay, and then you're going to do the noble gas notation. You're going to go to the previous noble gas, in this case xenon, and you're going to notice that xenon has 54 electrons. So you're going to notice that it goes from 1s2 all the way to 5p6. So instead of writing all of that, you place all that notation in brackets with xenon, and then you continue what is left with whatever is left. And that's the noble gas notation for Mercury. And then using the SPDF notation, as we did the same for sodium, you go circle by circle, placing all those electrons on the energy levels. Be very careful because the third energy level, the third circle, you have 2 plus 6 plus 10. You must have a total of 18 electrons on the third circle or on the third energy level. So on the fourth one, make sure you have 2 plus 6, 8, plus 10, 18, plus 14, 32 on the third circle. I'm sorry, on the fourth circle. On the fourth circle, you must have 32 electrons because if you add all the superscripts that are on the energy level number 4, you will reach to those 32 electrons. And then the fifth energy level will have 18 in the same way, so try it again slowly. And you will need a sixth circle with only 2 electrons because that's the biggest number or the biggest energy level. Okay, I hope, we're missing the, I'm sorry, we are missing the Lewis dot diagram. It will only have 2 electrons because the last shell is the sixth one with 2 electrons. I hope this was useful. See you later. Bye.